Okay, so let's mix it up a little bit. We're going to switch gears from strong acids and bases to weak acids and bases. And this is where I think you're going to have, I'm just going to jump into a couple of problems. And yes, there'll be problems like this on your test, and there's homework problems like this. Good attitude. But we're going to, this to me, like part one, this is part 3 lecture. To me, kind of part 1 and part 3 go together, but we needed part 2 when you guys did all that kind of going back and forth between the hydrogen, the hydroxide, ion concentration, and the pH and the pOH. So it all kind of goes together. So, can't decide. When I see a problem like this, and you're going to see it on the next slide, and I can't remember what my builds do, but you're going to see me write the equilibrium for this weak acid. Now, does it say to write the equilibrium for this weak acid? Well, I don't know if the test is going to step you through that or not, but I'm gonna. So it's a weak acid. It's called niacin. Acid be a proton donor. Does this look like a good candidate? I'm just going to kick off that hydrogen, and on the other side, I'm going to show that without that. So it looks like this. HC6H4. I know there's multiple H's, but it's going to be this guy that's going to go. NO2. In equilibrium with H plus that C6H4NO2 minus 1.
Is there a name for that big molecule?
This thing would be, we're going to, actually in part 3, we're going to call it actually the conjugate base of this weak acid.
Okay.
So it's conjugate. So WA, of course, stands for weak acid versus SA stands for strong acids. So you can't go wrong then writing the Ka expression. You totally can't, because actually I've seen this problem when we're going to use that next on a slide coming up. So the ionization of this weak acid, we can write it in equilibrium. It's always the products divided by the reactants raised their stoichiometric coefficients. It's everything we learned in Unit 3. So it's the hydrogen ion concentration, that conjugate of the weak acid, that C6H4NO2 minus 1, divided by the molar concentration of, I call this the unionized weak acid, okay? Molar concentration of the stuff that didn't break apart, C6H4NO2. So that kind of gets you started. So somewhere in the margin, I'm going to write down the other thing. So it says a solution of 0.012 molar. Now, of this, solution of 0.012 molar of the niacin. I'm going to actually write that under here, 0.012 molar, but I'm going to say that that's the initial. I'll just write it initial. Or I could write, does that make sense? It's the initial stuff. And then it says, after the dust is settled, you go ahead and you stick in your pH probe, which you'll be doing some in tomorrow's lab. You stick in your probe and you come up with a pH, so I'm going to put it on the hydrogen ion concentration if that's okay. I'm going to say pH is equal to, and you guys had plenty of work going back and forth between this pH and that hydrogen ion concentration. You definitely can do that. Okay? I'm going to go ahead and say that's at equilibrium. So that's kind of the scenario we have. What is the value of Ka? Well, we can get to the value of Ka if we know the equilibrium concentration of the hydrogen ion, which you can get from the pH, the equilibrium concentration of the conjugate base, that's that anion there, and the equilibrium concentration of this stuff, what's left over after some of it ionizes. Honestly, this to me is just really another ice chart. Okay, so I know this is what I wrote on the board already. So what do I mean by ice chart? Well, you know, if you're like, I think Mrs. Snipe said I'm supposed to do one of these. And I think some of you guys don't use ice charts, which is fine. You just kind of, and I don't know if Carl does either. I like it to organize it. So across I'll put my headings, the molar concentration of the C6H4NO2. That's the weak acid, the non-ionized version of the weak acid. The molar concentration of the hydrogen ion, and the molar concentration of the conjugate base, C6H4NO2 minus 1. Initial change at equilibrium. Well, I already told you the initial this is the initial, right? 0.012 molar. And do you see where I can get the equilibrium concentration from my pH of my hydrogen ion? Then I can use stoichiometry to kind of go back and pick up, well, I'll just go ahead and do it. Okay, so those are initial concentrations. And it seems kind of strange. This slide is reminding me I'm going to put 0 here and 0 here, because I'm going to say it started out as that 0.012 molar of your weak acid. You didn't have any hydrogen ion, which you had a little bit because of autoionization, but not much. And you definitely didn't have any of that C6H4NO2 minus. So we know how we can take that pH. We can take 10 raised to the negative 3.39, allow ourselves 2 significant figures in the molar concentration of the hydrogen ion, and then bada boom, that number goes right here. This is that 4.1 times 10 to the negative 4th. Well, the stoichiometry is a 1-to-1 here. So now we're ready to fill out our ice chart. To me, this was plus 4.1 times 10 to the minus 4th. And the stoichiometry is 1-to-1 here, plus 4.1 times 10 to the minus 4th, okay, minus 4.1 times 10 to the minus 4th, right? So I can do this one over here, 0 plus 4.1 times 10 to the minus 4th. That means the molar concentration of this thing, your conjugate base, is 4.1 times 10 to the minus 4th moles per liter. Now, if you put this in your calculator, okay, how do I say this? Well, since we're subtracting, we're going to take 0.012 minus 4.1 times 10 to the minus 4th. You have to round according to decimals. If I were to write this out, this is, what, negative 0.00, so 041. Does that look right? Okay, and the thing I'm adding it to is 0.012. I have to round according to decimals. So honestly, you buy that? Okay. So now we're ready to put those in our Ka expression and to get the Ka. Now, the fact that we put this is 0 up here is a little lying, because we have autoionization going on. That means just auto means by itself, ionization means breaking apart of water to form H plus and OH minus. And we talked about what is the molar concentration of your hydrogen ion at 25 degrees Celsius Monday, and we came up with 7.0 times 10 to the minus 7th moles per liter. If I were to put that here, it wouldn't change our answer appreciably. All right. So, yep, we're good with that. This just actually kind of says what I did on my ice chart a minute ago. Do you guys see where, because of stoichiometry, we got this from the pH, and be careful with stoichiometry. If this had been twice as much of this C6H4NO2 that is formed along with your H+, you would have had to jack that up by a factor of 2, so just be careful. the equilibrium concentration of your weak acid in equilibrium with the H plus and its conjugate base, that would be what you started with, 0.012 moles per liter, minus what reacted, which was that 0.00041 moles per liter, which, like I showed you, by the time you round it, you're going to get, it's like not subtracting anything. And this is very common to have basically most of the weak acid, in this case the niacin, most of it stays unionized. So it only ionizes to a certain extent. Any questions about those? And then you're almost done. We just have to take those equilibrium concentrations and plug them back into your Ka expression. And it looks like this. Where in the numerator we have two terms of that 4.1 times 10 to the minus 4th. Two terms because one is for the hydrogen ion and the other is for that C6H4NO2 minus. In the denominator you have the molar concentration of the unionized niacin, which is that 0.012. Multiply it out, round it to two significant figures, you get a Ka value of 4.1 times 10 to the minus 5th. 1.4 times 10 to the minus 5th. Thank you. So that's not too bad. Very good. We have these problems. I'll take a quick look. I did look at these this morning, so that's always good. Looks like this. So you have some Chem 1 stuff to kind of do on the front end in some cases, but it's very similar. And I want to emphasize that if you had the paragraph up there without the weak acid equilibrium, you have to just get in the habit of writing that equilibrium for that weak acid. Propionic acid is going to kick off hydrogen, and it's going to be that last one over there. Okay, notice you kind of see it on the other side without that hydrogen. The only, I don't know if it's necessarily a catch here, but it says it gives the moles of the weak acid and it gives the volume. So you have to take the moles divided by the volume to get molarity. And honestly, that's a good habit to get into because when you work these problems, it's all about molarity, not moles, molarity. Okay, Ka equilibrium constants don't work with moles. So you're going to have to do that in the front end, and then my other hints kind of are, let's see, you don't even have to do the whole pH to the hydrogen ion concentration. Now remember, and I kind of told you, it's your problem, not mine, but notice that in this equilibrium, the way it's been done for you is they're going with the hydronium ion instead of the hydrogen ion. It's the same thing. Okay, it is the same thing, they're interchangeable. So, but other than that, it's very similar to what we did. Stoichiometry is one across the board, which makes it a little boring. So here's my ice table. You'll get the initial molar concentration when you divide the moles by the volume. Don't forget you have to convert the milliliters to liters. Have that work for you. The final molar concentration, the hydronium ion was given here, and that will be actually the change also in that propionic acid, what we're going to call the conjugate base over here. It's the stoichiometry is the same. That's what's going to be subtracted here. Once you get your three equilibrium concentrations, you put it back into your Ka expression to get your Ka. All right, the next one, it's even a little more on the front end. You have to convert grams per liter to molarity. Grams per liter to molarity. You can do it. You're given the formula of the weak acid, okay? Molar mass, right? In this case, you're given the pH, which this is kind of like what we had to do in the example we did. You have to take the pH, convert it to hydrogen ion concentration for your ice table. So, I think that's my hint. That's it. just be careful. Again, we have a stoichiometry of 1 across the board. Just make sure that, like, if the stoichiometry is anything other than 1, you know, you're going to have to adjust your changes here. A lot of people tired today. Maybe it's that smoke out there. It's like, I know. Okay, what else do we got? Okay, so I just want to do this next part to the next assignment slide, because then I kind of want to give you a little bit of time to do those. Now this changes it up a little bit. How does this change it up a little bit? Well, if you don't mind, I'm going to go over there and I'm going to write it's probably on the next slide, but I'm going to write the equilibrium constant expression for that weak acid. So kicking off a proton, write the Ka expression, get ready for, I know I'm going to use an ice table here. So, acetic acid, CH3COOH, is in equilibrium. I'll put WA for weak acid, so I'll do a 2A arrow here. I'll write CH3COO, and then I'm going to kick off that proton, or that hydrogen, so it looks like this. And then I'm going to go ahead and write the Ka expression. It's the molar concentration. I've had students call this CHO. Molar concentration of the CH3COO minus, and that actually does have a name. That's the acetate ion, times the molar concentration of the H plus divided by the molar concentration of the weak acid that didn't ionize. That's CH3COOH. I'll put little e's there because they're in equilibrium. And I'll go ahead and write my ice table. Initial, change, and at equilibrium. I have 3 columns. The first one is for the weak acid, the unionized weak acid, CH3COO minus, that's the acetate ion, and then the hydrogen ion over here. And then it says we're supposed to go for the hydrogen ion concentration, so question mark, and then we're supposed to take that hydrogen ion concentration to pH. We can totally do that. You guys did that for the homework that's due today. So does this make sense? Whenever it gives the molarity of your weak acid, and this took me a while, I don't necessarily struggle, but when they make up that's your initial molar concentration of this. So 0.10 moles per liter. And a certain amount of it ionizes to break apart to give you your acetate ion and your hydrogen ion. In this case, Ka is given 1.8 times 10 to the minus 5th. Okay? So this is one of those where, how does this work? Yep. This is one of those where, well, I'll show you. Well, let's just go ahead and do it this way. Do you guys buy this? What are these? 0, right? We're good with that? Let's see. If I go ahead and make X the amount of weak base, or excuse me, weak acid that ionizes, what are these two then?
Plus X.
Yep. Okay, so let's go ahead. At equilibrium, we have 0.10 minus X of your weak acid. We have X of your weak base, or, well, conjugate base, and we have X of your hydrogen ion. Let's go ahead and take those over here. Ka then is equal to, in the numerator we have X, and the denominator we have 0.10 minus X. So good? And for those of you who love the quadratic, then you just need to go ahead and boil it down to standard form and solve for X, and then you have the pH. But I'm going to show you another simplifying assumption that I'm going to expect you to use. Okay, so this sort of problem, like I said, you're going to want to get in the habit of writing the weak acid equilibrium, this expression, right? The equilibrium and then the Ka expression. far, so good. And then it looks like this. Again, some of y'all, when you're solving it, you kind of think not like a table like this, but kind of linear like this. If this is the situation, if we let X be equal to the amount of the weak acid that ionizes, then at equilibrium, your hydrogen ion will be equal to X. At equilibrium, that acetate ion will also be equal to X. And then at equilibrium, the amount of your unionized weak acid is going to be 0.10 minus X. So this is the same thing as that bottom row. And this is the same slide I did before, whereas when we put a 0 up here for the hydrogen ion concentration, the initial concentration is 0. That's sort of a lie. That because of autoionization, it's initially 1 times 10 to the minus 7, but it's really not going to mess up these sort of problems, okay? So this is the ice table that I have here. Okay, so I think we're probably good about this. So this is your Ka equation. Kind of showing the molar concentration of the hydrogen ion and the acetate ion, and the bottom is the molar concentration of your unionized acetic acid. Well, I mentioned a simplifying assumption. That all this does is combine the numerator, those two terms of X, and makes it squared. And we did a simplifying assumption before with our insoluble salts. So you could use the quadratic, but if we assume X is significantly smaller, if X is significantly smaller than the initial molar concentration of your weak acid, okay, then life becomes easier. If that's the case, then when we take 0.10 minus X, if X is a lot smaller than 0.10, that simply becomes 0.10. And then if we revisit our Ka expression, okay, now our Ka expression, I'll go ahead and write it over here if that's okay. Now your Ka, which we know the value for, is equal to X squared over 0.10, which feels kind of weird, but it's true. And we can definitely it's going to involve using the square root, but we can definitely get to X then. So this says, well, when is that a good thing to do? Well, in general, if the Ka of your weak acid, remember this is HB is just our weak acid. In this case, HB is our CH3COOH. Okay? If that Ka, take it times 100, so let's see, 1.8 times 10 to the negative 5th times 100 is 1.8 times 10 to the negative 3rd. Okay? Yeah. Take that times 100. Okay? If your molar concentration, which in this case is 0.10, is greater than 1.8 times 10 to the negative 3rd, then it's probably going to work for you. Does that make sense? In this case, we're looking at 0.10 is this, and over here we have 1.8 times 10 to the negative 3rd. So if that inequality is right, then your simplifying assumption is going to be fine. All that means is that your Ka is pretty darn small. The amount that ionizes, generally speaking, is pretty low. And that's what your simplifying assumption is. So it becomes this. So we crisscross. Of course, X squared is equal to 1.8 times 10 to the minus 6th. Take the square root of that. And ta-da! 2 sig figs. You're getting a value of X of 0.0013. And by definition, as we set it up, X is the molar concentration of our hydrogen ion, which is exactly what we're after. It's magic. Not really magical. So then we just need to, that was the first of 2 tasks, and then we need to go ahead and we're going to what? Take the log of that base 10 times minus 1. Negative log. Oh, this in green actually says if you were to use the quadratic, the real solution would actually, in this case, give you the exact same number, which is kind of nice. So here we go to get to pH. We're going to apply the P function, which is negative log base 10 of the hydrogen ion concentration, molar concentration, which is 0.0013. And then don't forget, I've been trying to kind of get you guys ready that whenever you take the log of a number, you show the significant figures of the number you took the log of in trailing digits after the decimal. So 2 digits after the decimal is our 2 sig figs. Okay? Any questions about that? They're kind of fun. Okay, so let's take a quick look at these. See, I told you I'd get out of here. This is how far I wanted to get. Because this is a good breaking point. Okay, so what do you think? Weak acid, HNO2. HNO3 is a strong acid. HNO2 is a weak acid. So you're going to want to write the equilibrium and the Ka expression and all that. And you're supposed to come up with the hydrogen ion concentration, or the hydronium, it's the same thing, and the pH. So, can't remember what I had for hints. Oh my goodness. Okay. So that's all my hints. It's basically doing what we did here. Okay. Again, you don't have to use an ice table, but you have to show me your logic, how you work the problem. Okay, if you don't. And, notice in this case, we're going to apply the simplifying assumption. Just like I did a minute ago, you can kind of see from this ice table that we're going to get equilibrium concentrations in terms of X. Okay, that's going to give us, well, if I went ahead and left this denominator 0.143 minus X, we'd have to use the quadratic. But the simplifying assumption, how did I say it? If 0.1, let's see. Oh, sorry. If X is significantly less than 0.143, then 0.143 minus X is 0.143.
And we'll just look up that Ka from the back of the book
Yes.
for HNO2.
Yep. Yep. And I think the back of the book, or they're probably in the slides in part 1 too, I think, if you got really good eyesight. So, yep, but definitely. And then here's the second one. It's dealing with phenylacetic acid, which all you need to know is it kicks off a proton on the other side. Okay, so I would write the Ka expression, which I don't have it up here, do I? But I would. It's very similar. What is, oh, notice that A says, what's the molar concentration? Not of the hydrogen ion, but of that thing I've been calling the conjugate base, the polyatomic anion on the product side. Okay, you should be able to do that similar to what we did here. And then the problem with B is it takes the same equilibrium, it switches it up. What is the initial concentration of the weak acid? So you got 2 ice tables, I think. Right, this one looks like this. Another weak acid, write the equilibrium and then the Ka expression. Yeah, like you said, Mike, I have look up here. All of them you look up. They have a very similar pattern. You'd be like, well, how come I need to do so many of them? I don't know. To get it under your belt. Okay, these I think are very similar.
There will be problems like this in the test in these problems, you said?
There will be yeah, you can count on it. Yeah. all my tests are kind of like that, like homework, what I drag you through, that's what you see on the test. Now this one, actually 39 is a little bit different because it asks for, sometimes students don't know what do you mean by degree of ionization? So, degree of ionization I kind of showed you for A. What does that mean? It means, in this case, I'm kind of putting it in terms of how much of the, like I've been calling the conjugate base, the polyatomic anion over there, you're gonna get molar concentration relative to the unionized stuff. Okay, that's degree of ionization. So 39 won't be, and you asked about the test, 39 isn't necessarily what I would put on the test. It's a good one to come to work on, but that one won't get a test. And it's odd, so you have the answers in the back of your book, under doc sharing. So any questions? Okay, so those will be due on Friday. Tomorrow,